Hello everyone. In this video lecture we are going to discuss about the observer design. When we considered the full state feedback design in the previous video, we assumed that all the states of the system were available for feedback at all times, because we were measuring them. We assume that they are available and we can measure them and apply the feedback gain and continue as we did. It's a good assumption for the control law, but generally we usually have only a subset of the states readily measurable and available for the feedback. So normally we don't have all the states available for the feedback. We don't have the value for them, or we don't have reading for them. If you want to have all the states available for feedback, it means that all those states should be measured with a sensor or sensor combinations. And in this case, the cost and complexity of the control system will increase as the number of the required sensors increases. So even in the situations where using extra sensors would be possible, it may not be cost effective to employ the extra sensors because the overall cost of the system will increase. Instead, we can use an approach in which we don't use the extra sensors, but we use kind of estimators in order to estimate the value for the states. This will be the case when we have the system completely observable. If the system is completely observable, which will be determined by looking at the observability matrix, as we will see later, with a given set of the outputs, then it will be possible to estimate the states which are not directly measured or observed. According to Leuenberger, the full state observer for a system given with this state space representation, x dot equal to ax plus bu and y is equal to cx, the observer is given by this expression here. X hat dot is equal to a times x hat plus b times u plus l times y minus cx hat. And y we already know that it's equal to c times x. So x hat here is the estimate of the state. So x hat is the estimate of the state x. And the aim of designing the observer would be to make the difference between x and x hat going to 0 or being quite small, especially for the transient part. And then they should become the same as each other. The matrix L here is called the observer gain matrix. So observer gain matrix, and our aim in designing the observer would be to determine the values for this matrix. It will be in the form of a vector indeed. Over here you can see the block diagram of the observer. It receives two inputs, u and y, and we have them here as well. So u is one input and y is the other input which comes from the system, and it generates or outputs x hat, which is the estimate of the state, and you can see it here. So y, indeed, x hat is multiplied by c, which gives us x hat here. Then we have the difference between the y hat, sorry, not x hat. X hat times c gives us y hat. And here we have the difference between the actual output and the estimated output. So y hat for us is estimated output based on the estimated state or x hat. And then here we have the error signal between the actual output and the estimated output, y tilde, which is used here. So x hat dot is equal to a times x hat plus b times u plus l times y tilde which is equal to y minus, we can call it y hat, or it's equal to cx minus cx hat. And eventually we can write it in the form of c times x minus x hat. So our aim here is to design L, the observer gain matrix, in order to make the difference between the x and x hat is small enough. Here you can see how the observer is receiving inputs, the u input, and y over here, it receives them, and eventually it creates x hat as an output, which could be used instead of the x itself in designing the controller. So for the full state feedback, we know that x should be multiplied by the controller gain k, and then it will be deducted from r. Here, instead of the x hat is being multiplied by the feedback gain k. Here again we have the system, the actual system, x dot equal to ax plus bu, y is equal to cx without the observer, and here we have the equations for the observer as we just explained. As I mentioned, the goal of the observer design is to provide an estimate x hat such that x hat goes towards x. So if the difference between these two becomes small as time goes towards infinity, we will have a proper observer. Here we have definition of the error, estimation error for the state. So E is equal to state error indeed is equal to x minus x hat, the actual state minus the estimate of the state. And now we see that we will see how to design L, how to find L in order to have that error going towards 0 as time goes towards infinity. This will be the case if our system is completely observable. So this is an important point to keep in mind. We need to have our system completely observable, and if that is the case, we can always find L such that the tracking error for the state estimation is asymptotically stable as desired. Here we have the error itself. We can take derivative of both sides with respect to time. It will give us E dot equal to x dot minus x hat dot, as we see here. And then we can replace x dot with ax plus bu, and x hat dot with ax hat plus bu plus L times y minus cx hat. And then if we replace them into this equation, we will have E dot equal to ax plus bu minus ax hat minus bu minus L times y minus cx hat. Plus bu and minus bu will drop, they will cancel each other. And then we will have E dot equal to a times x minus x hat minus L times cx minus cx hat, which could be rewritten in the form of a times x minus x hat minus L c times x minus x hat. And we know that x minus x hat is E, so we will have E dot equal to a times E minus LC times E, so we can rewrite it as A minus LC times E of t. And you can see it over here. So E dot is equal to A minus LC times E of t. And now for any initial value of the error, we can guarantee that the error will go towards 0 as t goes towards infinity if the characteristics equation that we get for this error system, which is obtained by finding the determinant of lambda I minus a minus lc equal to 0, it indeed gives us the pose of this error system if all of the roots are in the left half plane. And for that we need to find proper values for L, and this will be kind of similar to what we were doing in terms of the designing the full state feedback. If you remember, in designing the full state feedback, we were finding the determinant of lambda I minus a minus bk equal to 0, and you can see that they are kind of similar to each other. Over there we needed to find out the gain k, here we need to find out the gain L. But in both cases, by setting proper values for those gains, we should be able to place the closed loop pose of the system at proper place, or the pose for the observer at the proper place. Here we have an example. We have a system which is described in this way. X dot is equal to ax plus bu and y is equal to cx. By looking at the output, we can see that y will be equal to x1, and as a result, if we measure the output, we already have the value for the first state, but we don't have direct access to the second state, or x2. So we are going to design an observer in order to find out the value for x2 as well. To design the observer, we will start by checking the observability of the system to verify that the observer could be designed and constructed. If we have the A and C matrices as are provided, 2, 3, minus 1, 4, and C is equal to 1 and 0, then we can find out the observability matrix as C and C times A, and it will give us 1, 0, 2, 3. And we can see that this is a full rank matrix. The determinant is equal to 3. It is not equal to 0, so we can say that determinant of observability matrix is not 0, so the system is completely observable. The system is completely observable. It means that we can design the observer for this system. Then the next step would be to determine a desired characteristics equation for the observer. We have two states. As a result, the desired characteristics equation will be a polynomial of order 2, which means that we are going to place the pose for the observer somewhere like this in order to have a desired behavior. In this example, we are going to use zeta equal to 0.8 and omega n equal to 10, which will result in expected settling time of less than 0.5 seconds and the desired, let's say, overshoot. If we replace them, we will have the desired characteristics equation. So desired characteristics equation will be equal to lambda squared plus 16 lambda plus 100. And then on the other hand, for the observer, we have the characteristics equation obtained by finding the determinant of lambda I minus a minus lc. It will be given in this form. For L, we have it in the form of a column vector with L1 and L2 as the components. And then we can equate these two in order to obtain the values for L1 and L2. And you can see that we have 22 and 59 for the elements of the observable gain. Therefore, the observer will be given by the equation here. X hat dot is equal to A times X hat plus B times U plus L times Y minus Cx hat. And Cx hat will be equal to x1 hat, yeah, because we know that for C we have 1 and 0. So C times x hat will be equal to 1, 0 times x hat 1, x hat 2, and this will be equal to x1 hat. So that's why here we have x1 hat. For the estimation error now, we have E dot equal to A minus LC times E, and therefore E dot will be obtained as the equation here. So minus 23 minus 64 times E of t. And then we can now draw or depict the behavior of the error signals. We have two of them, E1 and E2, over time. And you can see them already drawn here. E1 and E2 are drawn here, the error signals that we have for the states. They start from some initial value, but over time, after let's say half a second, both of them have become 0. It means that after this point, the state and the estimate of the state will be almost the same as each other. Here you can see a piece of code which could be used. You can use different values for the initialization, for example. And in any case, you could see that after a short amount of time, the state and its estimate will become the same. If the number of the states increases, then we can refer to the Ackermann's formula as we were doing in designing the controller gain for the full state feedback to make the things simpler. Because if we have, let's say, 10 states, then finding the characteristics equation for the observer and then equating it with the desired characteristics equation wouldn't be easy. In this case, we consider the observer gain matrix L as a column vector with L1, L2 up to Ln elements. The desired observer characteristics equation will be in this form: lambda to the power of n plus beta 1 lambda to the power of n minus 1 plus beta n at the end. And these betas will be selected in order to meet the given performance characteristics for the observer. So you will indeed determine where to place the pose of the observer. We can say that these two will be the dominant one. If we have too many states, you can place the others somewhere else. Then we can find out the observer gain matrix directly by using the Ackermann's formula. L will be equal to P of A. So in the characteristics equation, we would need to replace lambda with A and then find out PA, as you can see here, and then multiply it by the inverse of the observability matrix. And you can see that the observability matrix should be invertible, otherwise we will not be able to find L. And then multiply it by a vector of zeros with a 1 at the end transposed. So it will be this will be indeed a column vector with zeros and 1 at the end. We can apply it to the same system that we had, to the same example. We have the characteristics equation equal to lambda squared plus 16 lambda plus 100. For A, we have 2, 3 minus 1, 4. So P of A will be obtained in this way. A squared plus 16A plus 100 times the identity matrix will give us PA. For the observability matrix, we have it in the form of C and CA, which is equal to 1, 0, 2, 3 as already calculated. And then the inverse of the observability matrix is obtained here. And we can use now Ackermann's formula to find out the L, the observer gain, by replacing PA and observability matrix inverted. And then after the calculations, we will get the same indeed values for the L, 22 and 59, as we had in the previous example indeed. Let me show you. Yeah, 22 and 59. So using the Ackermann's formula gave us exactly the same values as we did it manually by equating the characteristics equations for the observable and observer and the desired characteristics equation. Alright, so I think that's all for this video. I hope you have learned what the observer is and how the observer could be designed, and in which cases we can design the observable. We need to have the system completely observable. Thank you for watching and see you in the next video later.